Después que en el carro delivery que pasa. Solo dejarle eso.
Your microphone. You always need to make sure that your microphone is turned off. Only turn it on when you need to participate. So here, the weight multiplies and what is below, it's going to be divided. Okay, so when you move it from side, it's going to be doing the opposite operation. Here it was divided, it goes to multiply. And there you go. You have now your force applied on the part B, on the white piston. We have already answered 2 questions. Now I'm going to focus on the third one that says, what mass can the white piston lift? So I want to know what the mass that force represents. Okay, so what is the equation that relates the mass and has to do with the force? What equation relates the mass and the force? The force that the mass represents. Nothing? Guys, are you listening?
Density.
Okay, vamos a ver. Density gives me relates mass times divided by the volume. So density is not a force, okay? Not a force. And I want to know what mass does a force represent, okay? Remember that here in Pascal, we care about 2 things, force and area. Okay? So the mass is going to be related to a force, not to the area, okay? Now, what equation that is related to force is, you can use it to get the mass?
The weight.
Exactly, the weight, okay? So, if you know the weight, that was weird. If you know the weight, you know that the weight is calculated as mass times gravity, okay? So you know the weight because you got it in the step before, okay? You know the weight and you know the gravity, which means that you can easily isolate for the mass. So you say mass is going to be equal to the weight divided by the gravity. So we replace by the givens, okay? How much is this?
$632.
632. Now, in what units do we measure mass?
Kilograms.
Kilograms. That is correct. And with this, we finish. But
One question before you continue.
uh-huh.
What does the A mean? I forgot.
And the A,
Yes.
this one. That A.
No, the one that is under the F.
Ah, okay. This one.
No, the one under the F, like the one next to the one you highlighted.
Ah, okay. So FA, you mean this one right here?
Yes, and the one under.
Okay. Yes. That A means the position. Okay. So here, remember that you call in the hydraulic lift, you're going to like establish positions. Okay. One of the positions you can call A. That's why the A over there is because of that reason. It refers to, in that case, the small piston. The small piston, I'm going to call it position A. And the white piston is going to be the B, okay? The white piston is going to be in the position B. So this A from here refers to the piston located in the small area. Is it clear now?
Yes, miss. Thank you.
Okay, okay. Now, you might be wondering where the kilograms are coming from or not, okay? Some people ask and some people don't. But in my case, I just want you to know that this kilograms comes from this. You know, Newton is a compound unit, okay? Newton is a compound unit that is kilogram times meter over second square, okay? How do I get that? By definition, Newton, we use it to calculate, to express forces, okay? The definition of force says that it's mass times acceleration. Mass is measuring kilograms and acceleration is measuring meters per second squared. So from the definition of force, that's what we get, okay? The Newton in the end is kilogram per meter times meter per second squared. And you are dividing by meters over second squared. So this is where the kilogram comes from. Okay? That's why your final answer there, mass, is not in kilograms just because it is in kilograms because of a reason. What's the reason? The one that I just explained. Juan Fernando, your camera must be turned on and you can read to my class. So recall, we're gonna call those two positions as A and B. Okay, and from that, you're gonna be working, you're gonna be like getting the information according to the position that you have in the hydraulic lift. So we're now going to explain another example. I'm going to pause the video. Second example says a small piston of a hydraulic lift has an area of 0.2 square meters. A car weighing 1.2 times 10 force Newton sits on a rack mounted on the large piston. A large piston has an area of 0.9 meters square. Okay, so how large a force must be applied to the small piston to support the car? So in this exercise, no sketch is given. If the sketch is not given, what you have to do is just draw it. Okay, so every time you need to draw it, please just use a ruler. Okay, I was going to teach you like how to do it, but it's pretty simple. Okay, just I'm going to do it by hand, but you know that you have to use ruler. Just remember that one of the areas, okay, should be wider than the other. So what I do is just this. Okay. So here you have the wider area and the small area. and you can call the sides as A and B. Remember, A and B is necessary for this kind of exercises. Now, I don't need to do the sketch because I put it over there, okay? You don't need to do it, but in case that you need it, know that you can do it, okay? So, what I have to do in the first place is gather the information from the word problem. So it says, the small piston has an area of 0.2 meters to the second power. Now, I'm going to put A and B, okay? A and B. To what piston does it refer? A or B?
B.
B, okay? So I'm going to put the information where it corresponds. That is, the area in B is equal to 0.2 square meters, okay? I just put A and B where I want it, and then I'm going to call them individually. Lenny and Janice, your cameras are turned off. Okay. So then it says a car weighing 1.2 times 10 to the 4th Newton. Where am I going to put the information? It says sits on a rack mounted on the large piston. So where am I going to put that data? Over A or over B?
Over A.
Over A. Okay. That is 1.2 times 10 to the 4th power Newton. And this is the force that is applied on the point A. So I'm gonna call it FA. Okay, we already include this information. Now, the large piston has an area of 0.9 meters square meters. So where am I going to put that information of the area? In A or in B?
A.
So area in A is gonna be 0.9 square meters. And then it says, confirmation already put it there. Now it says, Miguel, your camera. How large a force must be applied on the small piston? So I need to find the force that is applied in the point B on the small piston. So the force in B is unknown. That is what I'm going to focus. Okay? I'm going to focus on that part. So having all the information organized like that, you can apply the Pascal's principle, who states that the pressure in A is equal to the pressure in B. And then you apply the formula. Force in part A is divided by the area of A is equal to the force in B divided by the area in B. So I need to find the force in B, which means that I'm going to be isolating FB. Okay, so AB in this case, the area B is doing a division. So when you change it to the other side of the equation, it's going to be doing a multiplication. Okay, so that is the first part of the isolation process that you need to do. So this will be FA multiplying AB divided by area A. This is going to be equal to force B, what you are looking for. Now just plug in the givens. Miguel, your camera, second call. FA, that is 1.2 times 10 to the 4th power Newton, is multiplying the area B. The area B is the small piston, and it is equal to 0.2 square meters. And I am dividing by the area A, which is 0.9 square meters. This is equal to force B. How much is this?
1,666.67.
Okay, in what units are we going to write this? Calderon? In what units are we going to write this?
Newtons.
Newton. You eliminate the square meters and the only remaining unit is going to be the Newton. As simple as that. So as you can see, this type of exercises need to be done in order. Okay, so be organized with your data and you will be doing just fine. Doubt on this exercise?
Me, so in always we're going to use this formula and we need to isolate for the one that we are looking for.
Exactly. So you're gonna put the information in the hydraulic lift and you will see where you need the information. And from that, you're going to isolate in the formula. The formula is not going to change. What is going to change is the isolation process.
Okay, thank you, Miss.
Okay. Okay, so far what we know about fluids. Okay, what do we know about fluids? We have been working so far with two types of fluids. Okay, static fluids and for this we have two examples. Okay, we work with static fluids in Archimedes principle. And also in Pascal principle. The idea is the fluids involved in those kind of exercises were not moving, okay, they were static. But today we're going to start with this one. Fluids in motion, okay? Fluids in motion. And we're going to start by talking about Bernoulli, okay? So we're gonna focus on Bernoulli's principle. So what I'm telling you right now is that so far we have been working with two types of exercises, Pascal and Archimedes, and both have in common that the fluids were static. In this case, we're going to consider motion. That means that the fluid actually is moving, it's changing position. Okay, so we're going to talk about fluids moving. That could be a river, for example. That could be an example of Bernoulli's principle, because in a river, you can see that the water flows, okay? Water flows at a certain velocity. Another example that you will find is water inside pipes, okay? In your faucet, for example, water is running and it's running, so that means motion. If it's motion, we're going to consider Bernoulli's principle. So for this, we're going to go into the third law, that is Bernoulli's principle. And we're going to focus on this equation. That is continuity equation. Wait. So what do we have in Bernoulli's principle? Imagine, I told you already, okay, to imagine a pipe. In pipe, what happens? Well, water is running in the pipe. Okay, so imagine that in a pipe, I have this equation. Imagine that in a pipe, I have the situation. I know it looks like a bottle. I know it looks like a bottle more than a pipe. But imagine I just cut a pipe like that. Okay? So imagine that we have this situation. It should have been black instead of blue. Okay. So what happened in a pipe? What do you notice in this part? What happens here? How was the pipe and how is after that portion?
It's smaller in the end.
So what happens means in that part that I'm pointing out, a reduction took place, okay? A reduction of the pipe, a reduction of the area at which water flows, okay? Or any other fluid. So take a look. Pipes work in this way. Pipes work like this. The fluid is going to pass through the pipe, okay? So it's going to travel like this. And then when this reduction occurs, water now is going to travel at a smaller area. Now, how is the fluid behaving? In the white part, okay, in the white part, the water behaves slower. Means that yes, it is moving, but at a slower rate, okay? So, okay, it is slower in that part. So I'm gonna call this part 1, okay? Side 1 of the pipe. And the narrow part, I'm going to call it side 2, okay? So what happens in the narrow part? Water begins to travel internally in the narrow part. It's going to travel faster. Because it's traveling faster means that there was a change in the motion, okay? So there was a change in the motion. So in Bernoulli's principle, in the continuity equation, we're gonna be, it establishes that the flow rate, Q, it is the flow rate, okay? Q in the part 1 is going to be the same as the flow rate in the part 2. Just like we did in hydraulic lift, right? That we related the two sides of the hydraulic lift, we're going to be doing the same here, but on a pipe. Okay. So this Q means flow rate, okay? Okay, so I'm going to compare the two flow rates, okay? The flow rate 1 and the flow rate 2. And it says it is the same. So I'm going to replace a flow rate by its definition. Flow rate can be calculated as the area of the pipe times the velocity, okay, of the flow. Okay, so area times velocity. And because I said, okay, I have the flow rate in 1, I'm going to replace it by the formula in the position 1. So this is going to be area in the position 1 times the velocity of the fluid in the position 1 is going to be equal to the area, position 2, times the velocity in 2. That is what we know as the continuity equation, okay? This is the continuity equation. Now, I'm going to do an example for this. Very simple example. but forgot to give you the definition of flow rate. Okay, so flow rate tells me about the amount of volume. When you multiply area and volume, you are multiplying area units like square meters times velocity. And the units for velocity are meters over second. So when you multiply the two, what you get is meter squared times meter is going to give you cubic meters and are going to be divided by the seconds. Now, this unit is the unit that I will use to measure the flow rate. And it tells me cubic meter is volume, okay? So it tells me the amount of volume that is passing through an area in a specific time. So the definition for flow rate is going to be the amount of volume per time unit. Okay, so that is the definition that we use for flow rate. Now, stop recording. Okay, there it goes. So right now, an example, I'm going to use the same pipe, okay? I will use the same pipe. And I say, I'm going just to say, I'm not going to write it, okay? Water is running through a pipe that has an area of 3.5 square meters, okay? It is running at a velocity of 3.8 meters over second square. After 4 meters, the pipe has a reduction in the area, okay? And now the area, the new area after the reduction is 0.25 square meters. Question: what is the velocity that the flow has after the reduction? Okay, so I'm going to calculate the velocity after the reduction took place. So I'm going to put the information in the positions that I need. So this is going to be my position 1, and this is my position 2, and I will organize the data as well, like that. So I put the subscripts. And then I just apply the formula. The continuity equation states that the flow rate is constant in every point in the pipe. So flow rate is the same in both points. So area 1 times velocity 1 is equal to area 2 times velocity 2. I want to find velocity 2, which means that I need to move area 2 off position. It's multiplying, so it goes to divide. So velocity 2 is going to be equal to area 1, velocity 1, divided by the area 2. We replace by the givens, and we have the area 1, which is 3.5 square meters, times the volume 1, that is velocity 1, so that is 3.8 meters per second square, divided by the area 2, that is 0.2.